Hello, Chem 1A. This is Chapter 11, Lecture Video 11. This is our last lecture video for this chapter, and we're going to continue talking about molecular orbital diagrams. In the last lecture video, we ended while showing you the diagram between an s orbital combining with another s orbital to give us our MO diagrams, or our molecular orbitals. But this is much more complex when you have a p orbital combining with another p orbital to give us our diagram. For instance, if you look at this diagram, we have a total of 6 molecular orbitals present in the center of our diagram. And this is actually due to the fact that whenever we combine a p orbital with another p orbital, well, you're actually combining 3 p orbitals with 3 different p orbitals. And because of this leads to a total of 6 different molecular orbitals, because each of those 3 p orbitals can constructively or destructively combine with one of the other 3 p orbitals, giving us a total of 6 different molecular orbitals. And so the general shape and look to our molecular orbital diagram will look something like this when we have a p orbital combination. However, there's actually 2 versions of this, and we'll get to the next one in just a second. We have degenerate orbitals when we combine p orbitals, where we have 2 molecular orbitals at the same energy level. Like with these pi bonding orbitals, here's our sigma bonding, here's our pi anti-bonding, and our sigma anti-bonding. Again, if you see an asterisk, you know that that's an anti-bonding orbital. This molecular orbital actually only works for diatomics involving boron, carbon, and nitrogen. So this version of p orbitals overlapping or combining is for these 3 types of diatomic molecules. Let's look at the diagram for the next 2, which looks something like this. So this is the other p orbital overlap, and what you might notice is the major difference between these is these 2 bonding orbitals have flipped. So in the last diagram, the pi bonding orbital was the lowest energy, and the sigma bonding orbital was just above it. But in this version now, the sigma bonding orbital is lowest energy, and the pi bonding orbital is slightly higher in energy. This one works for molecules that are O2 and F2 molecules, and you should know which one to use and when. You do not need to memorize what these look like. I will provide you diagrams on the exam in the equation bank, so you just need to kind of know which version of the diagram to use for which type of diatomic molecule. So now that we've learned a little bit about molecular orbital diagrams, now let's talk about what you can do with them. One of the things we can do is we can calculate the bond order between the 2 atoms in the diatomic molecule using this equation, which is bonding electrons from the diagram minus antibonding electrons divided by 2. What this basically tells us is that as we add electrons to bonding molecular orbitals, this adds stability to the molecule. And if we add electrons to antibonding molecular orbitals, this will reduce the stability of the molecule. In other words, the larger your bond order, the more stable your molecule will be.
Look at our full complete diagrams. There are 2 different ways to draw our diagrams. Not just in terms of, boron, carbon, and nitrogen diatomics and oxygen and fluorine diatomics, but in other ways as well. Notice this is the 1s atomic orbitals overlapping, and this is the 2s. And this is our 2p for boron, carbon, and nitrogen on the right. The difference between this diagram and this diagram are that, one, we're dealing with oxygen and fluorine here, so these 2 flip-flopped. But in addition, you notice that there's no 1s. This is because we're only doing the valence shell here. And this is all electrons. It does not matter to me which version you use. If you don't want to use the 1s, That's totally fine. You can cross it out and only do these top ones. You cannot cross off the 2s though. That is not okay. You have to include the 2s. So you're either doing all the electrons or only the valence shell. Now we're only going to be dealing with diatomics in the first 2 rows of the periodic table. And if you have something like hydrogen, well, you shouldn't be doing any of these. You should only be doing the 1s because that's all it's got. And you shouldn't even be doing that. But if you have something like carbon or oxygen, then you need to be at least doing the 2s and the 2p. I hope that makes sense. But again, these diagrams will be provided, and I'm actually going to use the ones I give you on the test on the next slide to do some problems. So let's do.
All right, so let's do some example problems. The first thing you got to understand is that when we look at our diagrams, we have to combine all of them in one big thing normally. All right, so these are the 2 possible diagrams that we could have for most diatomics. Let's start with one where we don't need the entire diagram, He2, right? So if we're looking at He2, He2 really only has s electrons, which means we really only need one of the bottom kind of parts of the diagram. So we can kind of think about all this not being relevant, right? So if we look at He2, we need to make this diagram appropriate for He2. We'd write He here, He2 there, and He there. Now, how many electrons does He have? It has 2. So on the sides, I'm going to fill in with 2 electrons in each s orbital. Now that I know that I have 4 total electrons in He2, I can put them in the middle, 1 up, 1 down, 1 up, 1 down. Now I can calculate my bond order for He2. I can also state that this is a diamagnetic molecule because there are no unpaired electrons in the molecular orbital diagram, the middle part specifically. So let's calculate our bond order. We know our bond order is equal to the bonding electrons, which if we look at right here, there are 2 of, minus anti-bonding electrons right here, which there are also 2 of. We then divide this whole thing by 2, we get 0. So our bond order for He is equal to 0. Now, this basically tells us that there really isn't much of a bond in between the 2 He molecules, and as a general statement, He2 probably doesn't really actually exist because of that. Now, He2 is one of the less complex diatomics we could do. So let's talk about what happens when we have some slightly more complex diatomics. So with a molecule that's slightly more complex, like F2-1, we'd need to first decide which diagram to use. Now, I will provide exactly this image here that you see for these diagrams on your test in your equation bank. So this is all you're going to get. You're not going to be told which one to use. You need to kind of decide that for yourself. This diagram, because of its p orbital shape, or p orbital diagram, is going to service F2 and O2 diatomics, right? So if we have either of those, we're going to use the diagram on the left. For the diagram on the right, we do this for B2, C2, and N2. So since F2- is F2, we're going to use the diagram on the left. Now, at this point, we also have another decision to make. We can use this diagram in 2 ways. 1, we can use it for only valence electrons, or 2, we could use only the valence electrons present in the diagram. So again, all the electrons that F2- has, or just the valence electrons. Now let's do all the electrons first. And I'll do an example of just using the valence for the most of the problems on this slide. So if we do that, let's look at how we do this. So we need to figure out our electrons on the sides before we can do our electrons in the middle. Now, one of the 2 sides has to have a negative charge because we have F2 minus 1, that negative has to be placed somewhere. So I know F has 9 total electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. F minus has 10 total electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This gives me a total of 19 electrons to put in here. Because I have 9 on the left side, I have 10 on the right side. So going from the very bottom, 1 up, 1 down, 1 up, 1 down, that's 4, 5, 6, 7, 8, 9, 10, 11. Now according to Hund's rule, because these two orbitals are at equal energy, 12 goes there, then 13, 14, 15, 16, 17, 18, 19 electrons are now in my MO diagram for F2 minus 1. Now we can calculate the bond order, right? So our bond order calculation here would be all our bonding electrons. So let's count those. So we got 2, 4, 6, 8, 10 bonding electrons. So I have 10 bonding electrons. Let's count our anti-bonding electrons. 2, 4, 6, 8, 9. We then do that subtraction, divide by 2, we get 0.5 as our bond order for the F2 minus molecule. This really tells me that F2 minus is really a very unstable diatomic molecule. It doesn't even have a full bond holding it together. It might exist. It's very unstable, just due to the low bond order that we're seeing. We can also say conclusively that it is a paramagnetic compound because of its one unpaired electron, right? If you have one unpaired electron, then you're a paramagnetic compound. So it does have one, so it's paramagnetic. Okay, so let's look at another example. What about O2? So O2 still uses the diagram on the left. This time, instead of using all the electrons like we did in the last one, let's use just the valence electrons. So this time, just valence electrons are going to be used. If that's the case, then we can cross out this bottom MO diagram because 1s is going to be core electrons for oxygen. We're going to start with the 2s orbital. So we have an O here, an O here, and O2 there. We know that oxygen, we do this slightly differently. We don't count all the electrons oxygen has. Now we only use the valence electrons that oxygen has. So that really tells me that oxygen, we know, hopefully has 6 valence electrons. So we're going to put the 6 valence electrons on both sides. This tells me that I have 12 electrons that I can put in the middle of my diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just looking at the diagram, because I have these 2 unpaired electrons in the middle here, this tells me that O2 is a paramagnetic substance. And again, I can calculate its bond order. The bonding electrons here are going to be 2, 4, 6, 8 total bonding electrons, minus the anti-bonding 2, 4. If I divide this out, I get that the bond order here is going to be 2 for oxygen, which actually corresponds to, if you draw the Lewis structure, you'll see that there are a double bond holding the 2 oxygens together. So again, this all kind of corresponds. Okay, so it doesn't really matter whether you use all the electrons in the atoms or just the valence electrons. Do whatever one makes sense to you. You should know how to do the one that you want to do. I don't really care which one you choose at the end of the day. Either one is a totally acceptable way to solve these problems. Okay, so let's do O2 2 minus. So I'm just going to keep going with the valence electron, and I'm just going to add on to my diagram here. So if I have O2 2 minus, then that means both of these oxygens here that I've drawn have to be -1. You could also put it 2 minus on one of the oxygens. The real version is -1. I'd accept it if you put the -2 on one oxygen as well, but in reality, it's a -1 charge on both of the oxygens. This adds an extra electron to both sides of my diagram, and it adds 2 electrons to the middle of my diagram. So now I have to add 2 more to the top because I have a total 2 extra electrons in this molecule. Now, this changes the diagram significantly because it was a paramagnetic molecule for O2. Now it's a diamagnetic molecule since we have no unpaired electrons in our diagram. And again, we can calculate our bond order here. Bond order is going to be equal to our bonding electrons, 2, 4, 6, 8 still, minus our anti-bonding electrons, 2, 4, 6, divided by 2. This gives me a bond order of 1 instead of 2. So we see a decrease in our bond order because we added electrons to an anti-bonding orbital. Okay, so let's do one more example. N2, 2+. Now, this molecule is going to be using this diagram over here now. And so we need to put nitrogen on both sides up top. So N and N and N2, but it's N2, 2+, so I'm going to put a +1 on both nitrogens. And then that gives me my 2+ overall on the top. Now, again, I'm just going to use the valence electrons in nitrogen. So I know that nitrogen, when it's not charged, has 5 valence electrons, but because of the +1, nitrogen's only going to have 4 valence electrons, which looks like that on that side and like this on this side. This gives me a total of 8 valence electrons I can put in the center. So 1, 2, 3, 4, 5, 6, 7, 8. Now, if we want to calculate our bond order for nitrogen, it's going to be equal to our bonding electrons, 2, 4, 6, minus our anti-bonding electrons, 2, divided by 2. This gives me a bond order of 2. Now, N2, 2+ is also a diamagnetic substance because there are no unpaired electrons in our molecular orbitals. And it has a bond order of 2. Now, one question I could also in addition ask is, great, which one of these is the most stable? Now, in this example, it would kind of be a toss-up between oxygen and N2, 2+, because they have the same bond order. Generally, on a test, you're only going to be really asked a question like this when there's a clear winner. One of the bond orders is going to be the largest. That's going to be the most stable of the molecules, and so that's the one that we will pick for the most stable of the selection. All right, if you have any questions at all, please do not hesitate to reach out. I'm always happy to help set up a Zoom meeting with me or just come to my office hours in Zoom.